Hello everyone, welcome back to Deviations. In the last videos, we talked about how we could find the maximum and minimum values of polynomial functions and trigonometric functions with the extreme value theorem and Fermat's theorem and the closed interval method. Well, we are going to be talking about some new theorems in the next couple of videos, the first of which is Rolle's theorem. So this is going to be a very theory-heavy video where we're going to be covering some proofs, and it should be nice. We're leading up to a really important theorem called the mean value theorem, which we will be talking about in the next video. As always, I recommend you fresh up on differentiation before getting started with Rolle's theorem. But otherwise, let's get started. So we are going to begin with the actual theorem that we're talking about. So this is the actual Rolle's theorem. So Rolle's theorem states that if I have a continuous function on AB called f, and it's differentiable on the open interval AB, and f of a equals f of b, so maybe I could draw a picture of what this function looks like. So if I have an x-axis here, and I have a and b, and I have a function that looks something like that, Rolle's theorem says that there is a c on AB such that f prime of c equals 0. So I'm going to have a local maximum somewhere in here. So that's what Rolle's theorem says for us. Okay, so we have three cases for Rolle's theorem. So let's take a peek at those cases. So the first case of Rolle's theorem says that f of x equals k. So it's a constant. So that means that our derivative is going to be 0. So c can be taken anywhere on AB, because if I have a horizontal line, then I'm going to have just a horizontal line where everywhere is 0. So I don't really have any local max or minimum values. Okay, then the second case is where f of x is greater than f of a for x and AB. So that means that the extreme value theorem says that f is going to have a max value on AB, and since f of b equals f of a, it must have a max value c on the interval AB, and that means that f then has a local maximum at c and is differentiable at c, and that means that f prime of c will be 0 by Fermat's theorem. Okay, so now let's look at the third case. So the third case says that if f of x is less than f of a for x and AB, the extreme value theorem once again says that f of x has a minimum in the closed interval AB. Since f of a equals f of b, f attains a minimum at c on the interval AB, and f of c will once again be 0 by Fermat's theorem. All right, so those are the three cases for Rolle's theorem that we are going to be using, and that's really what it's about. So now let's cover an example of Rolle's theorem. So this is going to be a proof with Rolle's theorem. So we're going to prove that x cubed plus x minus 1 equals 0 has only one real root. Okay, so one real root. So to do this, we are going to take a peek at f of 0 and f of 1. So f of 0 equals negative 1, which is less than 0, and f of 1 equals 1, which is greater than 0. So we have an area that's bigger than 0, and an area that's less than 0, between 0 and 1. All right, so we're going to use this. So we're going to say that the intermediate value theorem states that between 0 and 1, there's a number c where f of c equals 0. Okay, so we are going to have f of c equals 0. So what they're saying is if I have my graph here, and I have 2 points here on my function that I know are there, the intermediate value theorem says that I'm going to have somewhere here where I'm going to have a 0 point. Okay, so now we're going to try a contradictory proof with Rolle's theorem. So let's suppose that two roots existed. Then that means that f of a equals 0 equals f of b. And f is continuous on AB and differentiable on AB. Thus, there is a c between a and b where f prime of c equals 0. All right, so Now that's a contradictory proof with Rolle's theorem. Now let's take a look at the actual derivative of our polynomial here. So the derivative of x cubed plus x minus 1 is f prime of x equals 3x squared plus 1. And we are going to set that greater than or equal to 1 for all x. So that's greater than or equal to 1 for all x. That means that f can't be 0, so we don't have a 0 there. So that's a contradiction of this clause up here. So we have a contradiction. So that means that the equation can only have one root. All right, so that's our proof that a cubic here, that cubic polynomial only has one real root, one place where it crosses the x-axis. And that's how we can really use Rolle's theorem. Of course, there are easier examples, but I thought it would be nice to dive in with a harder example to get you prepared for what's to come, because we're going to be starting next video with the mean value theorem, which is kind of an extension of Rolle's theorem, which is going to be very powerful for us in Unit 3. All right, thank you for watching. Please like and subscribe, and we will see you in the next video. Bye-bye.